Here we are, good morning. It's the physics video lecture. Once again, physics 105B, video lecture 38. So we're wrapping up the Hamiltonian Mechanics. I think I'm going to return to that phase space discussion we had last time, maybe try to make it a little more clear. Then I'll talk about something that leads beyond what we're going to cover this semester, but kind of an outlook you might do in grad school. So, back to phase space. And, it's a conserved Hamiltonian. And our example with the physical pendulum is a good one. That's the one I'm going to talk about. Maybe get an even better picture this time. So let's go ahead and write that Hamiltonian down again. So we had the physical pendulum, and this thing can rotate the full 360 degrees, and then some. So what was the Hamiltonian? We had p sub theta squared over 2m, and then we had plus mgd and potential energy 1 minus cos theta. They're thinking do full 360 degrees if we want. There's the angle theta. Try to make sure that's what the there. Yeah, that'll work. Good. So we wanted to make the phase portrait, and I went ahead and put the 1 back in here because then for small theta, we ended up with the theta squared over 2, and we just had a classic harmonic oscillator. So small oscillations are pretty clear. I'll even call it H small oscillations. P theta squared over 2m plus 1/2 mgd theta squared. So the phase portrait for this one, of course, is really clear because it's just our harmonic oscillator, theta, p sub theta. And as we'd seen before, these are ellipses. And so for each, they're concentric ellipses, and each energy value, each value of the Hamiltonian, the larger ellipse. Okay. And you study this a bit more, you see they're all clockwise. And since it's a pendulum that has an equilibrium point when it's hanging straight down, this is the characteristic phase portrait for a stable equilibrium point. Then we had this general expression here. And this general expression, let's go ahead and solve for p sub theta. We can do that here too, but this one we need, so to speak. So p sub theta, we're going to have plus minus, we get square root there. So we've got, and this was moment of inertia. Go ahead, moment of inertia. Yeah. So we've got H, I'll call it E, minus mgd cos theta. Then over the side, 2i, should let myself a little room. We've got this. So we've got 2i, and take the square root. And the plus minus is either the top or bottom half of the phase portrait. So constructing this again, time with a little more room on each side, we can go pi minus pi, 2 pi minus 2 pi. And then for this phase portrait, theta is theta. We of course inherit this one for small oscillations right here. But at the point where the angle is pi and we're down here on the axis, that is the unstable equilibrium of something standing there on its head, so to speak. Okay? And so that's actually a special curve, because this unstable equilibrium is just a point, just as the stable equilibrium is just a point in phase space. This curve here I'll do in a different color separates, and it two typical regimes, and we could repeat this curve on and on as well. So pi is an unstable equilibrium, 2 pi is a stable equilibrium, and then 3 pi, we'll just do it here on the right side. 3 pi, these are supposed to be symmetric. So this curve here, not an ellipse anymore, is certainly easily available from this expression if you have the right value of the energy, namely 2 times mgd. Okay. So this blue curve, I may not have been quite clear about it. This one does not actually have any vector arrows on it. It separates 2 different regimes. Remember, this is just an increasing energy, concentric, as you go out. Strictly speaking, they're ellipses in the limit of small energies, but as you go up, it's still going to be this kind of an oval. Now, if you have an energy greater, so inside here, let's put this here, inside E, H equals E is less than, for my expression there, 2mgd. Okay. Difference between the thing hanging down the bottom and inverted. Okay. And then outside, H equals E is greater to mgd. This curve here, when E is equal to 2mgd, is the energy of this object, although it's not moving, it's just standing on its head. So any energy greater than this, how about we use a different color, because we can, we'll have a curve. So this next energy is slightly bigger. Okay. And this is available out of this expression here. Energy is slightly bigger than 2mgd. And remember, the vectors of the field, here I'll do one here, right, of Hamilton's equations are tangent to these curves. Okay. So here, for this energy slightly greater than 2mgd, we would have the vector coming in and going out. Okay. And ditto on this side. And one of these would be clockwise and one of them would be counterclockwise. Okay. So yeah, but this vector, which are tangent to these curves that you can get right here, they comprise that they comprise that typical picture of the vector field corresponding to an unstable equilibrium. So this here is a stable equilibrium, and this over here, and then I'll just draw it for, to kind of isolate it. The unstable equilibrium is, we'll use blue, is the one that's coming in like this. So that's why you have a vector field that looks like this. You see where it came from. But the actual blue line here, the one that separates the two regimes, isn't actually tangent to the actual vector field. It's always infinitesimally more energy on the one side or less energy on the other. Good, so this is your unstable equilibrium. And that's just what we did last time, repeated it. Maybe it's a little more clear now. And then, yeah, set that up here. And these arrows that I'm drawing are, of course, the vectors that you get from Hamilton's equations. So, from this Hamiltonian here, for a given energy. Good. So that's why Hamiltonian mechanics can be referred to as geometry in phase space. Because, especially in terms of all the qualitative aspects of the solutions, they're given by the behavior of that vector field. These points here, the stable equilibrium, the unstable equilibrium, those are critical points in a dynamical system. And then otherwise, when it's just smoothly flowing around here, then it's just a smooth vector field. It doesn't mean you can easily integrate it, but at the qualitative level, we can say things about it. So right now we have three types of motion. Motion about a stable equilibrium, unstable equilibrium, and then this is the general motion that's just repeating itself. So, I'll just wrap that up or rewrite that once again. So the vectors QP, so this is a 2n dimensional velocity vector. When I say velocity, I mean the motion of the vector QP, the endpoint of that 2n dimensional vector in phase space. And that was your dH and P on the one hand, your minus dH dQ on the other. So 2n dimensional phase space, vectors in the 2n dimensional phase space. These vectors are tangent to corresponding phase curves. In phase space, as we just drew up there. Okay, so I referred to it as flowing, and this next concept, the phase flow, it's really a way of looking at the system. So we're going to be in phase space, and now we'll just draw our 2n dimensional phase space like that. And we now know that a point in phase space is just an initial condition. So it gives position and momenta, and of course that belongs to a corresponding energy. It's just a point in phase space. It's an initial condition, but it's also just part of the motion. So if you treat this as an initial condition Q0, P0. Okay, so we've got this point Q0, P0. Then the solution that belongs to that initial condition is called the phase flow. So I'm just going to have it, for the sake of argument, going off in that direction next. So the phase flow is the motion of a system that corresponds to that initial condition. So it's the solution. We're discussing it as though we know the solution. Okay. Phase flow. Solution Q P of T corresponding to a particular initial condition. To an initial condition Q0, P0, like that. 2 dimensions, 2 n dimensions, however you want to look at it. So that's called the phase flow. And now I'm going to draw a larger harmonic oscillator once again. I'm just going to draw a larger version of this and discuss an interesting aspect of this phase flow. So we're using as our example the harmonic oscillator because we know that solution very well. Okay. So again, just to have everything up here, H equals P squared over 2m plus K Q squared over 2. There's our QP phase space. We're just talking about the behavior around the stable equilibrium. And for different values of the energy, we just have different amplitude clockwise ellipses. Okay. You know, I didn't want these ellipses to look that circular. To make our point, let's draw them a bit more elongated. So QP once again, but I'm just going to draw them like this. There's our stable equilibrium. Okay. They're ellipses, we can do what we want, right? We can make them as flat as we want, as long as they're concentric. Okay. And make them more concentric. Okay, here's the point. For any we can take a region of phase space, and in that region there are all of these initial conditions, right? They're continuously distributed, and then we could follow this entire region. So we could say, what does the phase flow do to this entire region of phase space? And because it is a, I choose a pretty squashed ellipse, this region is going to change shape as it gets carried around, but due to the true periodicity of the harmonic oscillator, when it goes around the entire circuit, it's going to land right back on top of itself. But on its journey, it's going to be, let's say it's elongated here, it's going to be squished into a different shape here. You guys figure it out. Okay. So the shape is going to change as it gets carried through phase space, but a theorem that I'm going to demonstrate says that the volume in phase space in this picture here, that area, remains constant. Okay. So we're talking about the phase flow, and so this phase flow carries a region as though it were a fluid that's just swirling around here. Phase flow carries a region of phase space. Or we'll just say it operates on the region of phase space. And the theorem that we're going to look at says that this phase flow preserves volume, which is to say this phase fluid is incompressible, so to speak. So the theorem, the phase flow preserves volume. And like I said, in my picture here, it means that as we carry this region around the harmonic oscillator phase portrait, the shape changes. Okay, the shape changes, but the volume, or in this picture, the surface area does not change. So the proof is trivial in one sense. I know a very involved proof, but I'm going to do one that invokes something out of fluid mechanics, and I'll owe you the little discussion of fluid mechanics at the very least. I want to do quite a bit of fluid mechanics this semester, but it doesn't look like we're going to do a whole lot. Be that as it may. So the phase flow preserves volume, and the proof is that the divergence of an incompressible fluid vanishes. Or actually, we're going to use this incompressible fluid so in fluid mechanics, so this is kind of parenthetical. We would say the divergence of the velocity field equals 0, which we're going to prove, we'll definitely get to prove that this semester. I only need an hour to do that, or first hour. But how about in Hamiltonian mechanics? In Hamiltonian mechanics, this is our velocity vector, okay? This time derivative of QP. It's not Q over P, right? That's the two n-dimensional vector. So we're going to make use of Hamilton's equations so we're making use of this. I'll prove this later. So here we're trying to do the divergence of P dot Q dot, and we're doing Q on top, okay. Divergence of Q dot P dot. So what is that equal to? Does that actually vanish? Well, this divergence we could say is d qi sum over I of the qi dot plus the sum over pi of pi dot, okay? Because those are the two n components, so let's each one 1 to n. Those are two n components of this divergence, and this is, because of Hamilton's equations, d over d qi dot is d h d pi. And over here we have d over dpi, and minus dh dqi. So this is a feature, sum over I, of Hamiltonian mechanics, that these things cancel one by one. So it's with the minus sign, second derivatives q p pq. So these are equal to 0. So the phase flow preserving volume is then used in thermodynamics and statistical mechanics, which is also then based on Hamiltonian mechanics, statistical mechanics in particular. So that's a theorem that you'll use at some point, and then you'll know where it came from. And it's going to depend on this fact here. It can be, by the way, it can be shown without recourse to fluid mechanics, which is a big proof in its own right. But I was thinking this would be a good reason for us to get into talking about fluids as well. So that's as far as I'm going to take it in Hamiltonian mechanics. Let's see how we're doing time-wise. Phase flow. So when we say the phase flow preserves volume, we're really saying that, you know, the motion of a region of phase space, or its mapping under the influence of the Hamilton's equations, you know, representative of the dynamical system. That motion preserves, in this picture, the surface area of any particular region of phase space. We'll leave it at that because we'll pick up with new topics in the coming days. And I have a couple, and I have time to do a few fluid mechanics, wanted to do more, but we'll see how far we get. Okay, good. We'll leave it at that and see you guys next time.